Hello, I am blackboardLM teacher, and today we are going into the world of speculative decoding, a technique that makes large language models run much faster. Our goal is to understand how we can turn a slow, heavy model into a fast one by using a clever little helper. We will first look at why models are slow by default, meet our two main characters, and then see how the math works out to speed things up. Does this plan sound good to you? Great. Let's start by looking at why models are slow to begin with, the generation bottleneck. Most large language models are autoregressive, which is a fancy way of saying they generate text one single word at a time. To produce just one word, the computer must move every single one of those billions of parameters from its memory into its processor. Imagine using a massive freight train just to deliver a single postcard. The train is the model, and the postcard is the word. Most of the time and energy is spent just moving the train. Because of this, the processor sits idle, waiting for data to arrive. Does it make sense why generating words one by one is so inefficient for these giant models? You are absolutely right that we must generate text word by word. The secret is that we don't make the giant model do the heavy lifting for every single guess. Meet our two main characters. On the left, we have the draft model. This is a tiny version of an AI, maybe only a fraction of the size of the giant one. It is like a fast-talking assistant who is often right, but sometimes makes mistakes. Because this draft model is so small, it can quickly shout out a few words in a row without waiting for that massive freight train of data we talked about. It creates a speculative draft of the next few words. Now, here is the magic part. We give that entire draft to the giant model. Because of how computer chips work, checking those 3 or 4 words at once takes the giant model almost the exact same amount of time as generating just one word from scratch. It is like a professor grade-checking a student's homework. Does it make sense that checking a draft is much faster for the expert than writing the whole thing from scratch? That is the perfect question. It feels like doing 5 times the work should take 5 times the time. But in the world of computer chips, the math is fast, but the movement of data is very slow. Imagine our giant model is like a master chef in a kitchen. The model weights are the recipe. The recipe is kept in a pantry far away. The bottleneck, the part that takes the most time, is walking to that pantry to fetch the heavy recipe books. Whether you want to cook 1 order or 5 orders of the same dish, you still only walk to the pantry once. Since the kitchen has thousands of tiny chefs or cores, they can all work on those 5 tokens at the same time once the recipe arrives. The math is so fast that the extra 4 tokens barely add any time at all. Does it help to think of the model weights as a recipe that we only want to fetch from the pantry once per batch? Now that we know the giant model can check multiple words at once for the price of one, let us see the actual logic of the check. This is the speculative speedup in action. Imagine our small assistant predicts the next three words, the, quick, and fox. It is just guessing based on its small brain. Now we send all three to the giant model in one single batch. The giant model runs the math. It agrees that the and quick are the most likely words. But for the third word, it disagrees. It wanted the word brown instead of fox. Here is the win. In the time it would usually take to generate just one word, the giant model has confirmed two words and corrected the third. Even when the assistant was wrong, we still got three correct words out of it. If the draft model is 70% accurate, can you see how this would make the overall generation much faster than going one by one? That is a very reasonable concern. You might worry that using a smaller, less capable assistant would make the final answer lower quality. But here's the secret. Speculative decoding is designed to be mathematically identical to running the big model alone. Think of the big model as a strict editor with total veto power. When the assistant suggests a word, the big model calculates the exact probability of that word based on its own superior knowledge. It only accepts the word if it fits its own internal rules. If the assistant is wrong, the big model rejects the word and replaces it with the word it would have chosen anyway. Because this rejection happens in the same hardware cycle as the verification, we lose no time compared to the old one-by-one method. We get the speed of the small model with the exact brains of the big model. Does it make sense how the big model acts as a filter to ensure the quality never drops? That is the brilliant part. When we say one cycle, we mean one trip to the pantry to get the model wheats. The big model can look at an entire sequence of words and calculate the probabilities for all of them at once because of how transformers are built. Normally, a model has to wait for its own output to decide what to do next. But here, the assistant has already provided the input. The big model takes all three words, the, quick, and fox, and feeds them into its processor simultaneously.
Inside the chip, the math for what comes after the and what comes after quick happens on different tiny circuits at the exact same time. The only slow part was getting the recipe from the pantry. Once the recipe is in the kitchen, these parallel circuits can check 100 words almost as fast as they can check one.
If the big model can check many words for the cost of one, why don't we just have the assistant guess 50 words at a time instead of just 3 or 4?
That is where we run into the law of diminishing returns. It is all about the probability of being right. Think of it like a chain of dominoes. If the assistant guesses 50 words, the odds that every single one is correct are almost zero. The moment the big model finds one mistake, the chain breaks. If word 3 is wrong, the draft for word 4 is completely irrelevant. Why? Because word 4 was predicted based on the assistant's incorrect word 3. Once the big model corrects word 3, we are on a new path, and those future guesses are useless. So, we usually only draft 3 to 5 tokens. It is the sweet spot where we get a great speed boost without wasting too much work. Does it make sense why one wrong guess at the start of a long draft makes the rest of the draft useless?